Let's determine the truth table and the logic statement for this circuit. So inputs to a digital circuit are either 0 or 1, and we have two inputs A and B. We have one output X. So we want to know, for all combinations of inputs A and B, what can we get out at X? Because A and B can take on values of 0 or 1, we have four combinations: 0, 0, 0, 1, 1, 0, and 1, 1. So when I have a circuit like this and I need to find the truth table, I like to mark some intermediate steps. How do I choose them? Well, whenever something happens, I put in a new step. So for example, here A and B are entering an OR gate, and there's going to be some output, so I'll label that C. Then C goes through this NOT gate, so I'll label this D. And after this AND gate, I'll label my value E. So first we'll determine what the values are at C for these inputs A and B. So A and B are going into an OR gate, and C is the output, so C is equal to A or B. Writing this down will be useful later. So A or B. A or B is true when one or both of the inputs is true. So this is 0, 1, 1, 1. D is just equal to NOT. This is the symbol for NOT. Is equal to NOT C. So that's just the inverse of this. So we have 1, 0, 0, 0. E is equal to A and B. That's only 1 when both inputs are 1, so it'll only be 1 down here. So this is 1 and all these are 0. And then my final output X is equal to D or E. So if D or E is true or both, I mark 1. So 1, 0 gives me 1, 0, 0 gives me 0, 0, 1 gives me 1. So what operation is this? Well, it's 1 when the inputs are equal to each other. If this had said 0, 1, 1, 0, that would be an exclusive OR. So this is a NOT XOR. But let's write down the logic statement for this. So I like to work backwards when I do these. So we want to get an expression for X in terms of A and B. So I just start with what we had for X, D or E. D is not C, and E was A and B. So that's A and B. C was A or B, so this is not A or B, or A and B.